If you set a strip of magnesium ribbon on fire, it combusts in a flash of dazzling white light. The solid metal transforms completely, leaving behind a brittle white powder. According to the law of conservation of mass, the total amount of matter present before a reaction must equal the amount left after. Atoms are never created or destroyed in a chemical reaction. They only rearrange themselves. This skeletal equation shows how that reaction reads on paper. We start with one magnesium atom and two oxygen atoms on the left, but on the right side, the product, magnesium oxide, only contains one oxygen atom. Mathematically, an entire atom is missing. To reconcile the math with the physical reality, we have to balance the equation. The most reliable way to do this without losing track of your elements is a strict system called the box and table method. Let's apply this system to a more complex reaction. This equation shows iron reacting with water to form iron oxide and hydrogen gas. Step 1 is setting boundaries. We draw tight red boxes around every individual molecule on the board. Consider these boxes locked. The small subscript numbers inside define the exact chemical identity of each substance. You cannot alter them without changing the substance entirely. Step 2 is taking inventory. We build an accounting table next to our equation, split into reactants on the left and products on the right, to track our iron, hydrogen, and oxygen atoms. Counting the elements as they currently appear, we have one iron atom on the left and 3 on the right. Hydrogen is even at 2 and 2. Oxygen shows 1 on the left and 4 on the right. The table clearly shows the iron and oxygen counts do not match. As written, this equation represents a reaction that is physically impossible. We start balancing by targeting the most complex molecule on the board. Here, that's the iron oxide on the product side. It contains 4 oxygen atoms, while our reactant side only has the single oxygen atom trapped inside the water molecule. Since our boundaries are locked, our only tool is a whole number coefficient, a large 4 placed directly in front of the entire water molecule. We cannot simply write H2O4 inside the box to force a balance. That would invent a completely different, unstable chemical. We can only change the quantity of water molecules we have. By adding that coefficient, we multiply everything inside the box. Our reactant oxygen increases to 4, matching the products, but the coefficient also multiplies the hydrogen. 4 molecules times 2 atoms means we now have 8 hydrogen atoms on the left. Fixing the oxygen created a new imbalance with the hydrogen. This cascading effect is why keeping a strict tally is required. Looking at the updated chart, we have 8 hydrogen atoms entering the reaction, but only 2 exiting as products. We resolve this by placing a coefficient of 4 in front of the hydrogen gas product. 4 times 2 equals 8, bringing hydrogen back into alignment. This leaves one final imbalance on the board. We need 3 iron atoms on the reactant side to match the 3 in our product. Notice that the iron on the reactant side stands entirely alone. This allows for a deliberate shortcut. Always leave single, isolated elements for your very last step. Modifying them won't disrupt the balance of any other atoms. We place a coefficient of 3 in front of the iron. The chart updates. A final review of our table confirms the numbers: 3 iron, 8 hydrogen, and 4 oxygen on both sides. The math is exact. To translate this math back to the physical world, we append physical states to the formulas. An S in parentheses designates solid iron and solid iron oxide, while a G indicates hydrogen gas. Additionally, when a gas is released during a reaction, it receives an upward-pointing arrow to show it is liberated from the mixture. We now have a mathematically verified, exact blueprint of how these molecules interact. By locking the chemical identities and carefully tallying the atoms, you prove the law of conservation of mass on paper every time you balance an equation. Now it's your turn. Here is a combustion reaction involving pentane and oxygen gas. The boxes are drawn and they're waiting for your coefficients. As you work through this, you may encounter one specific edge case. If you end up needing a fraction of an oxygen molecule to make your table work, apply a simple shortcut. Multiply every coefficient in the entire equation by 2 to achieve whole numbers. Set up your table, lock the molecules, and tally your atoms. The method is rigid, but it guarantees that you can successfully map out and understand absolutely any chemical reaction.